Alright, I know how excited we are about this, but let's try and rein in those emotions so we can talk about acids and bases, part 4. So we're going to talk about the common ion effect, buffered solutions, solubility and pH, and complex ion formation. So the first part of this is going to be the common ion effect. So let's take a look at a reaction here. This is hydrofluoric acid reacting with water, which produces H3O plus and fluorine F minus, or fluoride. So if we think of this reaction as it's laid out right here, this is going to be mostly reactants in this case. Since it's a weak acid, that means reaction lies far to the left. So reaction is driven farther to the left. So let's draw an arrow. Now, if we do something like, we've got this solution with this hydrofluoric acid, let's add some potassium fluoride to it. So Kf, we put Kf in there, and Kf is a solid. And Jonesy, old boy, let's draw some capitals, huh? So Kf, a solid, when we put that in, that ionizes into K plus and F minus. And since this is a very, very soluble salt, that means the reaction is going to be driven over, so there's no equilibrium here. So if we take a look at these two systems, which are happening in the exact same container, by adding this potassium fluoride, we've added potassium ions and we've added fluoride ions. And the fluoride ions are going to have the effect on the system. So those fluoride ions, that means you're going to be increasing the concentration of fluoride inside of this solution. So by adding the fluoride, it's going to drive the equilibrium even harder over to the left. So to begin with, this solution, when it was just the hydrofluoric acid, it had a pH, whatever that pH was. And the pH, of course, is due to the concentration of the H plus molecules. So if we add fluoride, that's going to drive the equilibrium even farther to the left, which is going to lower the concentration of the fluoride, which means that the pH will go up. So it's going to take this acidic compound, drive the equilibrium back, so it's going to end up using up these H3O pluses, which is going to lower the hydroxide ion concentrations, which is going to increase the pH. So we add something to an acidic solution and it changes the pH, even though this potassium fluoride itself is not acidic or basic, but it drives the equilibrium based upon Le Chatelier's principle. Right, same general idea. This is a basic system, though. So we have ammonia and water, which produces hydroxides and ammonium, and those hydroxides make this system a basic system. So if we take a salt like sodium or ammonium chloride, NH4Cl, and it experiences 100% dissociation as long as it's unsaturated, that's going to generate NH4 plus and Cl minuses inside of the solution. And once again, those NH4 pluses right there, since we're generating more of those, we're going to increase the concentration of the NH4 plus. That will drive the equilibrium back to the left. So before you had OH concentrations, when it was just the ammonia in there, it had some amount of hydroxides. When you add in that NH4Cl, this ammonium chloride, it's going to drive the equilibrium back, which is going to lower the concentration of the hydroxide, which means that the pH will go down as well. So we lower the hydroxides, pH goes down. It's going to become more acidic. Even though we didn't add something acidic to the solution, we're just driving the equilibrium away from the basic part, which makes the solution approach more towards neutrality. So really all these problems are is just a calculated effort for Le Chatelier's principle, where we figure out, okay, it's going to drive the equilibrium, it's going to change stuff, let's figure out what the new stuff is. So here's an example. 450 milliliters of 1 molar formic acid is mixed with 250 milliliters of 0.4 molar sodium hydrogen carbonate, which is also known as sodium formate. And they're mixed at 25 degrees Celsius. We want to find the pH of this solution, and the Ka is 1.8 times 10 to the negative fourth. All right, step number 1 in a problem like this is going to be to find the initial molar concentrations of each species in the new solution. So if we take a look here, we're combining 450 milliliters with 250 milliliters. So before anything reacts, we're automatically going to be diluting both of these solutions. So let's take a look then at the 0.45 liters of the solution. And in that solution there is 1 mole of the HCO2H for every 1 liter. And that's going to give us then the moles of the solution. And if we just take that number of moles and divide it by the total number of liters, which would be, divide that by the number of new liters, which would be 0.7 liters. You just do that over 1. So liters cancels out. We're not canceling out anything there. We're just getting it into moles over liters. And so that's going to give us our new molarity, which is 0.64 molar. Okay, so that's our new concentration of the CHCO2H. 0.64 molar. Let's try and make a legitimate decimal point there, huh? Yeah, close enough. All right, let's take a look at the other solution. So 0.25 liters of solution. And we have 0.40 moles of sodium formate for every 1 liter. Liter cancels out liters, did it up there too. And we want to divide that by the new concentration, by the new volume, to get into molarity. And so that is 0.14 molar, and that is our sodium hydrogen formate. Okay, so since this will end up being an equilibrium problem, we're going to need to know the initial concentrations leading up to an ice table, of course. So right here are our initial concentrations of the formic acid and of the sodium formate. So let's remember those two. Hopefully you have them written down. And let me go ahead and hop to a blank screen. All right, let's take a look at, write down both of these equations. So HCO2H, that's formic acid, and formic acid is a weak acid, which means it will set up equilibrium between that and H plus HCO2 minus. The sodium formate, NaHCO2, that is a very, very soluble salt, so it's not going to set up equilibrium. It's just going to 100% dissociate to produce Na plus and HCO2 minus. What do you know? We've got a common ion here. So the formic acid produces this formate ion. The sodium formate also produces a formate ion. So that's going to end up driving the equilibrium back. So in order to find out what the pH of this solution is, we can't just do our typical Ka calculation based on the formic acid. We need to figure out based upon the driven back concentration, so this equilibrium being driven back to the left. So if we think about our ice table then, and let me switch things up real quick. Alright, so I just flopped those two equations so that our ice table is easier to line up with them. Okay, so the initial concentration of the formic acid, we figured that out in the previous slide, and we found it to be 0.64 molar. The initial concentration of H+, we're going to say, all right, so before this formic acid is associated at all, it's not going to generate any H+. And the sodium formate, this up here, it doesn't generate any H+, so we're not going to concern ourselves with that. All right, but then for the formate ion, so we're talking about the formic acid not yet dissociating, so we're not going to generate any of this yet. But the sodium formate, this is already completely dissociated, and so it produced some formate in there already. There's our common ion. Okay, so in the previous slide, we found out that the concentration of the NaHCO2 was 0.14 molar. Since that completely dissociates at a 1-to-1 ratio, that means the initial concentration of the formate is going to be 0.14. 100% dissociation, so it's going to generate 0.14 moles per liter of that guy. So in order for it to move over and generate a little bit of this H+, the formic acid is going to have to decrease. And just to be clear, when we're doing our ice table, we're just doing it for the formic acid equilibrium. So that it will decrease by X, H+ will increase by X, and CO2H will also have to increase by X. I just noticed I wrote those two flop back from each other where the H is. It's the same molecule. I just wrote the H on opposite ends. Sorry about that. Okay, so then at equilibrium, the concentration of the formate is going to be 0.64 minus X. H+ will just be plus X, and 0.14 plus X for the formate ion. Alright, we were told what the Ka was in the previous slide, or in the question. We were told that the Ka is 1.8 times 10 to the negative fourth. Sorry, kind of cramming it up in there. Okay, sorry, that's 1.8 times 10 to the negative fourth. So if we take that value and plug it in for plus X, 1.8 or 0.14 plus 1.8 times 10 to the negative fourth, that still equals 0.14. So that means this plus X is not necessary. If we do the same thing, take the Ka value and plug it in for this negative X, we'll see that that negative X doesn't matter either. So that's going to simplify our equation a lot. So let's take these values to a new slide, the 0.64, the plus X, and the 0.14, and let's plug them into the Ka equation. Alright, so Ka is going to equal the concentration of the H plus times the concentration of the formate, HCO2 minus, divided by the concentration of the undissociated HCO2H, formic acid. And the value for that is 1.8 times 10 to the negative 4. Alright, so let's take our numbers and plug it in. 1.8 times 10 to the negative 4. That's going to be equal to our unknown yet concentration of H plus times the concentration of HCO2, which we said was 0.14, divided by the concentration of undissociated formic acid, which we said was 0.64. Okay, I'll assume you can solve for H plus yourself. Just rearrange the equation. And when we do that, what we're going to get for the concentration of H plus should be 8.2 times 10 to the negative fourth. And pH, which should be the negative log of the concentration of H plus, so the negative log of 8.2 times 10 to the negative fourth, would wind up being 3.09. So there we go. That's how you would solve a pH calculation based upon a weak acid and some kind of soluble salt that's going to generate a common ion. Alright, let's do another example problem. This one's worded a bit different and it's actually solved a lot different. Same concept though of common ions. So how many moles of sodium hypoiodite, I'm going to mess up that name a lot during this video, must be added to 250 milliliters of 0.2 molar hypoiodous acid to produce a solution with a pH of 7.5. Let's assume that the volume does not change when we combine these guys. Okay, so the first thing that we need to do when we look at this problem is we need to figure out if we want a pH of 7.5, how many moles of H plus is that, or what's the concentration of H plus in that solution? So pH of 7.5, if we wanted to figure out what the H plus concentration, so our target concentration of H plus, it would be 10 raised to the negative 7.5, and that gives us a H plus concentration of 3 times 10 to the negative 8th. Notice how I just write 3 because this number right here, the 7.5, only has one sig fig. So our target H plus concentration, the H plus concentration that we're trying to achieve, is 3 times 10 to the negative 8th. Alright, let's go to a blank screen and carry that number over there. So let's take a look at the Ka. calculation for this guy. So Ka is going to be equal to the concentration of H plus times the concentration of OI minus, all divided by the concentration of Hoi. All right, so we know what the concentration of Hoi is. That's the, of Hoi. The Hoi is going to be the 0.2 molar from the original question. We know what our target concentration of H plus is. That's 3 times 10 to the negative 8th. What we're looking for then is how much NaOI we need to add. And so to figure that out, we're going to need to know what concentration of OI minus is. Just for the sake of knowing, HOI is going to be our weak acid, and that's setting up equilibrium as H plus and hypoiodite. And then our salt that we're talking about, the sodium hypoiodite, is NaOI, and that goes through 100% dissociation to generate Na plus and OI minus. So there's our common ion that we're talking about. We looked at, if you flip back to the previous example, you're going to see that like the HOI, it's a weak acid. So even though it dissociates from the 0.2 molar, when you subtract the amount that it dissociates by from the original 0.2 molar, it's not going to change by that much. So what that means is the concentration of HOI at equilibrium is still going to be 0.2 molar. So that means right in here we can plug in the 0.2 molar. We know what our target H plus concentration is, and since this isn't changing, we can just take that target number and plug it in for there. What we're solving for then is the target concentration of this OI minus. And that OI minus is going to come from this, from our sodium iodide, sodium hypoiodite. All right, so the value of Ka was 1 times 10 to the negative 4th. It was 2 times 10 to the negative 11th. Okay, our target concentration of H plus we said was 3 times 10 to the negative 8th. We don't know what our hypoiodite is, and our HOI is 0.20. So if we rearrange that and solve it for x, and x would be our concentration of OI minus, and I'll trust that you guys can do that kind of algebra on your own at home. It tells us that our concentration that we're shooting for is 1 times 10, not my day, to the negative 4th molar. So that means for every liter we're going to need 1.1 times 10 to the negative 4th molar of this hypoiodite. The question asks us how many moles we need, though not what our concentration is. So let's clear this board, turn that into moles. So we have 0.25 liters of solution. We said that the volume's not going to change, and we need to have 1 times 10 to the negative 4th moles for every 1 liter. Liters cancels out liters. And that tells us we're going to need 3 times 10 to the negative 5th moles of NaOI. If you wanted to be real fancy about it, you can convert that over to grams then, and that would be how many grams of sodium hypoiodite you would have to add to your hypoiodous acid in order to generate a pH of 7.5. All right, try some other practice problems. I'm sure I assigned you guys some from the textbook of these common ion problems, because the next thing that we're going to talk about, common ions and buffers, is really important that you understand how to do common ion calculations in order to figure out buffers. So if this doesn't make sense to you, what we just learned, the buffering will make even less sense to you. So make sure you understand common ions before you go to the next video.